Alright, welcome back to Scholar's Draft, doing some math. Today we're going to be working on the other half of section 5.2, graphing polynomials. So, there's no real good trick. All we're going to do is plug in some values in an equation, and looking at our end behavior, whether it's opening, or whether it's going to infinity as we go right, or going to negative infinity. So, here we go. Number 1, x to the 4th minus 2. So if we read the directions, this is graph each polynomial by making a table. Use either direct or synthetic substitution. So direct substitution, you just plug your value into the equation. So I'm going to choose some values. And for these type of graphs, you want to choose at least 5 to 6 points. So usually you want to start on the negative side, and then you end up in the positive. So I'll choose some easy numbers like -2, -1, 0, 1, and 2. And it's a lot easier in this case to use direct substitution because there's only one x value, and doing x to the 4th is pretty easy for these numbers that we have. So -2 to the 4th is positive 16, minus 2 is 14. If I plug in -1, -1 to the 4th power is positive 1, minus 2 is -1. And then we plug in 0, 0 minus 2 is -2. And then we got -1, and then we got 14 again. So this is what it looks like. Go to our graph here. Hopefully you can see this in the video. So I'm going to go to -2, boom, boom, and then down or up 14. Well, that's pretty high up. So that's like here. And then -1, go all the way down to -1. And then 0 is -2. And then 1, -1, and then back to positive 14. So when we graph it, we obviously know where this is going. But we always remember our degree is even, and our coefficient is +1 is positive. So that means as x goes into infinity, y goes to infinity. As x goes to negative infinity, y still goes to positive infinity. Alright, so g of x equals x to the 5th plus x squared minus 4. You can still use direct or synthetic substitution for this one. I'm going to use synthetic just to show it off some more. So I'm going to still use the same values. Hopefully they work out well. So here we go. So here's, I'm plugging in -2 into the equation. And I'm going to look at all my coefficients. So remember, I'm doing synthetic substitution. Looking at my coefficient of my x to the 5th. So the number in front of x to the 5th is 1. Then I have no x to the 4th, no x to the 3rd, and then we have an x squared. And then we don't have an x to the 1st, but we have a constant. Okay? And then I'm going to drop down my first number, multiply it by my number here. So I have -2. Drop that down. 0 plus -2 is -2. Multiply that and get +4. Drop it down. 4 times -2 is -8. 1 plus -8 is -7. Then I have 0. Oh, -2 times -7 is +14. 0 plus 14 is 14. Then we got -28. -28 plus negative 4 is negative 32. So my y value here is negative 32. Okay. And then I'm going to show it off one more time. Negative 1. And I'm still up against 1, 0, 0, 1, 0, negative 4. So I'll bring down the first. 1 times negative 1 is negative 1. And then it becomes positive 1. Then it becomes negative 1. Negative 1 plus 1 is 0. 0 plus 0 is 0. 0 times negative 1 is 0. So we have negative 4. Okay, and then I'm going to use direct substitution for 0 because 0 plus 0 minus 4 is minus 4. And then 1 is negative 2. And then 2 is 32. So let's graph what we have. So 0, comma, negative 4. Boom. Negative 1 is also 4. One is negative 2. Or, whoops. I'm drawing on the wrong one. Erase. So let's start over. So 0 at 1, 2, 3, 4. Negative 1 is also 4. Positive 1 is 2. Negative 2. And then 2 is really high. And negative 2 is really low. Okay. So we look back at our chart, and this is a power to the 5th, so it's odd, and the coefficient is positive. So when we have an odd power and the leading coefficient is positive, as x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. So let's see what that graph looks like. Now, once you get familiar with x to the 5th, they actually do a little hump here. There we go. Next problem. Alright, number 3. So I'm going to go a little bit faster. I already calculated all our points using synthetic substitution. I'm going to show you another example of synthetic substitution just so you keep getting practice. But I'm going to look at the end behavior. So we have an odd degree. 3 is odd. And we have a negative leading coefficient. That means as x goes to the right, we're actually going to be going towards, my y value is going to be going down, so negative infinity. As x is going left, we're going to have positive infinity. Okay? And I'm just going to graph all these points here. So we have negative 2 super high, negative 1, 11. I'm just going to say that instead of 5, this is 11. And then 0, 5 would probably be around here. So I'm making up all the tick marks too. And then 1 is 5. Or at least in the y direction. Every tick mark is 2. My x direction is still 1 to 1. 2 is also 5. 3 is -1. So around here. And then 4 is -19. So that's when it starts to go really far down. So when you're using your own points, try to find one extreme. So like, for example, -2 goes to +29, and then 4 is when it goes down to the other extreme, -19. So this type of graph kind of looks something like this. It actually loops around like that. It goes down really high up. Don't worry about the loops. Just know that everything above cubic kind of has multiple humps sometimes. All right, let's show off that synthetic substitution again. This time I'm using -2 once more. So the leading coefficient in front of my x cubed is -1, and then x squared is 3, -2 for x, and then 5 for no x. Drop this down, -1, -2 times -1 is +2. 3 plus 2 is 5. 5 times -2 is -10. We get -12. Then we get +24. 24 plus 5 is 29. Okay. So that's... And then, of course, you would either use a calculator or use synthetic substitution. On your test, you will have to show all your work with synthetic substitution. It's not going to be either or. So make sure you show all your work. Make sure you practice this. All right, number 4. I'm going to go even quicker. Not show much at all, but after plugging these x values into that equation, I got these y values. So I'm going to go ahead and graph. So -2, comma, -32, -1, 9. And then we have 0, 0, 1, 7, 2, 0, and 3, -57. So it kind of looks like a little bit like a parabola. As x goes to the right, forever and ever and ever, my y value is -infinity, and then we have -infinity again as x goes to the left. So remember, negative leading coefficient, even degree means negative infinities. Alright, so I'm going to keep going on. Hopefully you copy that down. I'll just give you one more second. Alright, here we go. Next. 5. 2, xy. You got -2, -27. And this is just after calculations. 0, 7. 0, -7. And then 1, -3. And 2, 21. So notice every time I choose my x values, -2 starts off with a really low or high number, and then it gets closer and closer to 0-ish or closer to the middle, and then I always end with a number, so x equals 2, that also gives me a really high or low number. So here we go. Leading coefficient is a positive number, and then we have an odd, so this is going to be infinity, and negative infinity. And so negative 2 is all the way down here. Negative 1, negative 9, 0, negative 7, and then 1, negative 3, and then we got 221. So we got something like this that's going on. So don't draw your lines straight, make them a little curvy. Your cubic functions kind of always look something like this. Alright, number 6. This one would have took some trouble because we have that fraction there. But if I plug negative 3, I get 0. Negative 2, I get negative 20 over 3. If I plug in negative 1, I get negative 8 over 3. Plug in 0, I get 0. I get 1, I get negative 8, 3, 2, negative 20 over 3, and then 3, 0. So this is what it, if I were to test a few more points, it would probably be negative 4 and 4, and that's when we'll shoot up into the sky. To just show you the overall picture, what this kind of looks like. So we have 0, 0, we have negative 3, 0, and we have positive 3, 0. Negative 20 over 3 is about 6 2/3. So 6 2/3 is around kind of here. And then we have, what's next? 8/3. So that's 2 1/3. So around here. So this, and then copy it over. So this is where you get your W shape. This is what quartics are supposed to look like all the time. Now, I didn't make mine very curvy, but make sure yours is curvy. Because remember, straight V shapes are absolute values. It's supposed to be curvy. So that's what it kind of looks like. And once again, positive leading coefficient, even degree means infinity, infinity. Alright, let's move on to the next page. Alright, it's your favorite type, word problems. So the energy E in foot-pounds is in each square foot of a wave is given by the model E equals 0.029 s to the fourth, where s is the wind speed in knots. Graph the model by making a table for positive wind speeds. So graph the model, use the graph to estimate wind speed needed to generate a wave with 1,000 foot-pounds of energy per square foot. Be sure to label your graph. So I don't know if you can see my graph that well, probably because of my video quality, but you should see this solid line. And they made it easy for you because they gave you the formula. Bam. So my y-axis will be my energy. And you would always say in foot-pounds, or I meant you'd put in parentheses your units. And I would probably, on your sheet, I'd probably count by 100s. So this is my 2 tick marks. So I'd go 100, 200, and then so on and so forth. And then down here, I would go by 5s. So every 2 tick marks. I would go 5. And then this would be 10, 15, and so on and so forth. Why did I choose those? It's just something you have to get kind of familiar with. Sometimes you want to plug in points first, see how that goes. Just so you can get the overall representation of the graph. But let's plug in some values. So in this case, it'd be a lot easier to just do direct substitution. So here is my S value, which is wind speed. And we only want to use positive because that's what they said, positive wind speeds. And then our energy's right here. So of course, if there's no wind speed, there's no energy. Let's try 10. We get 29, 20. Plug that in equation using your calculator. 464. So 30. 2,349. So that's got skyrockets. So let's see if I can have something easier to work with. I'll try 5. So 5 is lower. Got 1.8. 125. So that's pretty low. Let's try a little bit higher again. Maybe above 10. Let's try 15. 146.8125. 2. There we go. 25. 1,302.8125. So we have a solid enough points to plot our graph. It's going to end up, let's get started at 0, 0. And then I'll have you graph the rest, but it should look like, so I'm going to do it up here. It should look something like this. Nothing special. And then there was something else in our question. We needed to use the graph to estimate wind speed. So if you graphed it kind of correctly, you could look at your graph and say that's like, oh, it's about 25 or something. Or just plug it in the equation. The energy we want is 1,000. And then we're looking for S. So 0.00 or 29 S to the 4th. So I would divide by 0.029 to both sides. And then I would take the 4th root. So, or you could do square root twice. And then you should get S, S is about 24.2. So that's that. Let's move on to the next problem. From 1987 to 2003, the number of indoor movie screens M in the United States can be modeled by that weird, crazy equation. Make a table of values to graph the function. So, number of movies. Movies. Type pen. And then years since 1987. So 0 would represent 87, 1 would be 88, 2 would be 89, and then you would go on to 2003. So my X values is pretty easy just because they give us the range 1987 to 2003. Movies, we kind of don't know until we start plugging values in. It's going to be high for sure because we're dealing with 21,000. So here we go. I'm going to punch in, I don't know, how many years is it? 16 years. I'll punch in 8 values, you punch in the other 8. But here we go. So T and M, I'll get the easy one, 0. Plug 0 into the equation, get 21,600. That's pretty easy. And then I would use a calculator. If you're using one of the TI-30s, you can put this into your calculator, a negative 11 times whatever your x value is, let's say 1. So 1 cubed plus 267 times 1 squared minus 592 times 1 plus 21,600. Now, if you punch that into the TI-30s or your graphing calculators or any calculator with some memory, well, first off, you'll get 21,264. But all you have to do is go back in the calculator and replace this values, all your t values, with your new number. So, for example, I'm going to plug 2 in there. So hopefully it's saved in your calculator. All you do is replace all your 1s with now 2s, and it'll make your calculations go faster. 21,396, 3, 21,930, 4, 22,800, 5, 23,940, 6, 25,284, 7, 26,766, 8, 28,320, and then you guys would keep going to, I don't know, 16. And then when you graph this, and have like, I don't know, 20,000 here, and then have like 30,000 somewhere up here, and then 40,000. And the reason why we're starting around 20,000 around 0, because most of our values start above, well, it does start above 21,600. And you'll probably get something that hopefully kind of looks like that. Maybe, let's erase that. Maybe something more like something like that. All right, that's it for now. Make sure you do the rest of those. You don't really have to, but it's good practice. Make sure you know how to do your synthetic substitution. In this case, synthetic substitution would not work out so well because we have really crazy coefficients like 11, 267, really big numbers, so you might as well have to use a calculator anyways. Synthetic substitution is usually good for low coefficient numbers, which tends to happen through most of our problems. Alright, bye.